Good morning, everyone. Thanks for showing up early for whatever this is going to be. I was kind of curious how many of you guys will have brought questions or topics that you want to hear about versus just going through some pre-planned problems. So, see a hand. So in the problems we're looking at like the abundance of an isotope calculating the atomic weight. So if we had an abundance and an atomic weight, we would just be using the usual multiplication sigma rules. And then it's a summation, so then we'd be adding those up. So we'd be just following the addition rule. I doubt we'd see a sigma problem tied into that kind of question. So the way the test usually works, there'll be a sigma question, right? There'll be a pretty obvious type question that you can see a lot. And then most of the other questions won't have like six things embedded into them. So I thought you'd see kind of a question where it also has one of these six things. You can think about it, it's an important part of the problem, but not one that you probably see with that. That helps. Yes?
Are there going to be any short response questions?
There will be no typing of words. Numerical entry, a few, but not words. So there's no spelling, no short answer. So it's all multiple choice or numerical entry. And the numerical entries will be, of the 20 questions, maybe like 3. Other questions? If there's certain topics anybody wants to hear about more than others, let's go here and then down front.
What conversion factors should we have memorized?
That's a good question. Not many of them. If you go to that module for the practice exams, you'll see the info sheet that you get has probably a couple. I actually haven't even looked at that info sheet. But if you go to modules, check that information out. In fact, I know you guys can't see the screen, but if you go to modules and go find the practice exam, it has the 12-10 exam 1 useful info. I just wanted to take a look. There's a periodic table there. We don't need Avogadro's number for this test. The joule units are given. That's really not something we need to know precisely or something we'll probably see either. There's some other conversions. They must be planning this for other classes. They actually give you the milliliter to cubic centimeter conversion, which was one I was saying to know. That's such an obvious one, though. I'm actually surprised they put that on there. They give the equation for kinetic energy, but we did not talk about calculating kinetic energy, so I would not worry about using that equation. If they were wise, they would take that one off, just because it's really not something we cover out of chapter 1 anymore. So topically, if you look at chapter 1, the very middle section, I think it's 1.4 on energy. We just wanted to briefly discuss the difference between kinetic versus potential energy. Kinetic's the energy of motion, potential is stored energy. But in terms of like stored energy and bonds being released to make new bonds, that balloon reaction, kind of thinking of potential energy being released. The temperature conversions are there. They give you the average atomic weight. Somebody had asked me if the average atomic weight equation would be given. I said, probably not. It's actually on here. So where that's the sum of the fraction of each isotope times its mass summed over all isotopes. If you need other conversions, if you look at this chart, like they don't give you the random conversions for like grams to, or kilograms to pounds or liters to gallons. Presumably, the test either doesn't need those conversion factors, or if they do, they'll put them in the problem. So the non-SI conversions, we will give you those. The main ones to know are the kilo, centi, using the prefixes. So being able to convert kilometers to meters, meters to centimeters, or also cubic meters to cubic centimeters to cubic millimeters with the cubic dimension. There's a couple problems we'll probably get to this morning that will go through that conversion. Yeah, so anions being neutralized with H+ ions. Let me add a page here. So the idea of what an acid is, let's take a step back just for like say HCl. So this is what HCl looks like. Don't worry about coming up with the Lewis dot diagram for it or dot structure. When this thing hits water, so when this thing is dissolved into water, it releases into H+ and chloride minus ions. In chapter 4, we'll write those as AQ. You can actually have HCl as a gas. You don't have to have this memorized. But the whole idea is seeing that that you have a molecule here. You have, a molecule where you have two atoms chemically bonded together, and then that bond's broken when the molecule in, say, the gas phase is bubbled into water, and then we get the ionization to H plus into chloride ion. And it's kind of like, this is the area that we kind of hit nomenclature at, is learning how to name a bunch of anions. But almost all those anions are capable of either reacting or being neutralized with H plus, and then going to the fully neutralized compound. So for example, if you took sulfate ion, you could neutralize this with two H plus ions to go to H2SO4. Now, we haven't exactly talked about chemical reactions yet. That's the topic for a little bit later today, and when we get into some chapter 3 topics, that's more of a topic for midterm 2. But you can sort of see here, we're just adding two H plus ions to neutralize that charge. And so then the thing that we get, the important detail out of chapter 2, is that H2SO4 is something that we would term to be an acid. So, and what we look for to call something an acid is we see what looks like H plus ions added onto an anion we learned how to name. And so then the key is, well, what's this anion? It's sulfate, and the 8s go to ic acid. And if it was like sulfite, so if it was SO3, so if we had H2SO3, then that would be sulfurous acid. If the original ion ends in ITE, it goes to OUS acid. And if you had something like HCl, a chloride, the ides go to hydroic acid. So hydrochloric, hydrobromic, hydroiodic, HF, hydrofluoric acid. So you're just looking, well, what's the name of this thing here? That's fluoride. It's been neutralized with H plus. And so acids, you can think, are the products of the neutralization with H plus ions. When you lead to a neutral compound, when you have a compound that's overall neutral in charge, we name it in this acid category. If we had only added one H plus to say sulfate, and we end up with HSO4 minus, we name this thing here, since it's still an anion, like an anion, and it's derived off of sulfate, so we call this one hydrogen sulfate. If we add, say, to the phosphate ion, let's say we add two H plus ions. We need 3 to go to the full acid, H3PO4, but if we take this, the H2PO4 minus, we call that dihydrogen phosphate. So here we just use the because we have 2, so dihydrogen and then phosphate. Now, the dihydrogen phosphate ion, the hydrogen sulfate ion, those aren't the most common to see on the test, so I wouldn't dwell a whole lot on those examples. There's probably more examples of nomenclature, of nuances of nomenclature that we don't have to worry too much about. Like if you look at the practice exams, you may have seen, especially with the Department's 2 practice exams, it's kind of light on naming. If you look at my practice exams, they're a little heavy on naming. To me, like, we're introducing a lot of different things with naming. We're trying to introduce different formulas, different classifications of compounds. There's even other ions I used to name that I don't really bother naming anymore. Like bromate was on a bunch. So if you look at my daily quizzes, you may have been confused by a bunch of like BRO2s or BRO3s. Just know that chlorate is ClO3 minus, and then bromate is BRO3 minus. And you would certainly never have to know that for the test. But in terms of the daily quizzes, where this was coming from is just like, this is chlorate, this is bromate. So you can name bromic acid, bromous acid, hydrobromous acid, very much the same as the chlorine examples. So nothing too, challenging for the exam in terms of what you have to know, other than just like learning that system. If you add a no, it's per, so BRO4 minus, ClO4 minus would be per chlorate, chlorite, hypochlorite, etc. So just kind of like knowing that system is probably more useful and helpful than the specific, memorization of all the goofy ions that maybe I used to have students go through and memorize. Okay, other topics? If there's anything at all, so I'll just start going through some of the questions from the packet here. All right, so let's take a look at this question here. So this diagram is just depicting nitrogen with the black sphere, hydrogen with the white spheres. What term applies to this substance? So we're looking at sort of the substance one molecule, but also the collection of molecules. So I have a collection of what looks like 4 molecules here. So I can see that these are, if I'm just like trying to classify what this is definitely a molecule because I have atoms bonded together. This is certainly a compound because I have 2 different elements mixed together. So this would be a molecular compound. I could call this a pure substance because there's only one thing present. And if I think about the homogeneity, is it uniform? If I have a pure substance, it's going to have to be uniform. So this is definitely uniform throughout, meaning is it like perfectly mixed together? If you just have one thing, if you just had like a container of water, it would appear to be uniform. Half the side of the container wouldn't look different than the other half. It's all water, it all looks the same. So uniform throughout would apply. Let's talk about non-variable composition in a minute, but molecule and compound apply as well. Variable composition means if you look at one composition of the matter, it's a different form than another piece. So if you had a mixture of 2 different compounds, a variable composition would mean if you had the ability to see the individual molecules, one molecule would have one collection of atoms and elements, and the other would have a different collection. So if you had a mixture of 2 different things, then you'd have a variable composition, so this is certainly a non-variable composition. So all those terms there apply. Some vocabulary things to think about from chapter 1, physical versus chemical reaction. The key detail is thinking, did the bonds actually change during the course of the reaction? So a chemical reaction should lead to a different set of bonds. If you can write out a reaction where you have reactants and products, that's an obvious example of a chemical reaction. But if you can think of something that takes place where you can't just easily flip and undo what had taken place, then it probably was a chemical reaction. Like when we exploded the balloon, we're not putting the balloon back together. We're not putting the things in the chemicals that were inside of the balloon, the hydrogen and oxygen. We're not getting back to those just by flipping a switch somewhere. So that's the result of a chemical reaction. So explosions, combustions, fires, those are going to be the result of a chemical reaction. If we then think about just phase changes, if we talk about the day when I froze the racquetball and broke it, I just did a physical reaction because I just broke that into pieces. I didn't really change the nature of I didn't like explode the thing. It looked like it exploded, but it just broke apart because it was really hard from the freezing. So physical reactions just lead to changes in phase, maybe solid, liquid to gas. I mentioned before, sometimes we might write like ice melting this way as if it's a chemical reaction, when it's really just a physical change. It's just a physical change. You can think the easy ability to go forward and backwards here just by changing temperature is a good indication that that's a physical and not chemical reaction. Pure substance versus mixtures. I mean, obviously you can have like pure water, you can put things in it, have a mixture. Mixtures can be heterogeneous or homogeneous. So homogeneous is perfectly mixed, heterogeneous has different layers. So heterogeneous is like oil and vinegar that have settled. Homogeneous mixture would be like salt water that's fully dissolved. So the difference between some of these words here, like an element is just one of the elements in the periodic table. Only one of the groups, the noble gases, exists as monoatomic gases, that being the helium, neon, argon group of elements. Every other element either exists as solid, where you have things like iron bonded together through metallic bonding, or you have things like nitrogen bonded to itself to make N2. A weird question that sometimes comes up every now and then is, if we say N2, and you just say, okay, I have nitrogen, maybe it's a gas, or maybe you have a container that looks like you have N2 molecules within it, is that an element? And it is. Like an element isn't just considered if you have one single atom. An element is just when you have just one single atom. So this is definitely an element. Sometimes we call N2 the elemental form of nitrogen, or the most stable elemental form of nitrogen is N2 gas, O2, oxygen gas. And so in terms of naming real quick, so like when I say like nitrogen, a lot of times I mean N2. Like when I say like, consider the element oxygen, well, it exists naturally as O2 molecules. Do you have to have the diatomics memorized? Probably not, but it's probably not, it might be useful just to hear me say it, because I don't think I've actually said this yet, but if you start with nitrogen, go across N2, O2, F2, and then go down Cl2, Br2, I2, and then throw in H2. So those are the 7 diatomic molecules. And the only key detail I think would be, and this maybe gets more important when we start writing reactions. And we start doing combustion reactions, we'll do one later, where you take something plus oxygen, and it's always O2, it's never just O. But it's just because that's how oxygen exists. It's like if I said take iron, like take a sample of iron and react it with something, you're thinking, well, iron exists naturally as a solid, so that's going to be its starting point. Okay, and so then compounds, 2 plus elements, make a compound, and then a molecule is just 2 plus atoms. And so, you know, H2 or N2, these are molecules but not compounds, but they're certainly elements. So H2 is an element, it's a molecule, but it's just not a compound because you have to have 2 elements present. Then you look at something like water. Water is a molecule, it's a compound, but it's obviously not a pure element. It's two different, it has 2 elements. And then intensive versus extensive property. The key detail here is that intensive is the characteristic property, meaning that's the one that depends on the substance, and that's the one that's not quantity dependent. The extensive property, this is just a simple quantity dependent property. And by quantity dependent, we mean it doesn't depend on the specific substance. Think of it like this. You can have a gram of water, you can have a gram of anything. You have a gram of ethanol, a gram of methanol, a gram of whatever the compound is. But only a certain compound will have a melting point of 0 degrees C and a boiling point of 100 degrees C. And it doesn't matter how much water you have, that's its physical property. So the properties that don't depend on the amount of substance or the intensive property, those are the ones we characterize properties with. And then the extensive properties are the things that just define how much of a substance is present. Now, the only confusing detail sometimes is that if you think of like mass for like say water, if you know the mass of water, you can infer or determine the volume of water because of the density of water is a known quantity. Because you might know the characteristic property, then you could calculate the volume given the mass and vice versa. Don't take that to mean that the mass and volume, though, are intensive properties. Like take ethanol. So ethanol versus water. You can have a gram of ethanol, a gram of water. They have different volumes because they have different densities. The characteristic properties, the density, the ratio of the mass to volume for a substance is unique to the substance. Most substances have different or unique or characteristic densities, but they can have any mass or any volume that you wish to have and pour into a container of, say, their liquids. Okay, that's some chapter 1 terms. Let's take a look at this question here. Now, the actual technique here being shown is mass spectrometer or mass spectrometry. The only thing I would really worry about here or try to understand that we use in this technique is that with this technique, with almost any substance, if it's an element, if it's a molecule, you can determine the precise atomic weight or molecular weight depending on what the substance is. And so in this example, they are using, looking at the isotopes of magnesium. So we're trying to determine, and this is the experiment that you use to try to determine the abundance of the different isotopes for a given element, in this case for magnesium. And so they're trying to say, well, which one of these appears to be correct in terms of the abundance of the isotopes? And so one of the things that we could look at is we could look at magnesium in the periodic tables. 24.3 is the average atomic weight. So that's the average atomic weight. Now that's kind of helpful because it gives us a sense of when I take the weighting of the different isotopes, they should average out to about 24.3. And so then another detail would be, well, let's actually just look at box 2 real quick and roll it out. So I look at box 2, I see a mass of 24 versus 26, and then a bigger mass at 25. So think of how that would work out with an average. So if you have like, say, 25% 24, 25% 26, but 50% 25, do you see how the average atomic weight would be about 25.0? So this would average out right to about 25.0 if we calculated an average atomic weight, and that's not the right atomic weight. We need to have abundances higher on the 24 side. So we need to have a higher abundance on the 24 in order for that average to be closer to 24. Think of it like this. If the atomic weight was 24.0, if the average atomic weight of magnesium was 24.01, it'd be like 99.9% 24. So we're 24.3. So we're definitely going to be more abundant in the 24 isotope. It's really looking, I think, like box 1 here is probably correct. We can also roll out box 4 because again, it's going to average out to 25, not 24.3. And then this box here is meant to show kind of one isotope having the most abundant mass around 24.3, but this now comes to a different topic, which is there's only certain masses that would be possible for a given isotopic mass. If we look at magnesium 24 versus 25 versus 26, those mass numbers imply 24 protons and neutrons, 25 protons and neutrons versus 26 protons and neutrons, where each of those have a mass of about 1 AMU. So the mass of a given isotope should be pretty close to a whole number. We mentioned before, you can't just add up the proton and neutron mass and get the mass of the atom because of nuclear stability. So it's usually right at that whole number or a little bit lower. Okay, and so we're not going to have a mass possible around 24.3 AMU. So the mass for magnesium 24 should be close to 24.0 AMU, for 25 to 25.0 AMU. And so that's how we can roll box 3 out. But that's kind of a weird question. I can say I didn't really like this question too much when we put this on a test a couple years ago, but I really do like the thought that we should probably know that most of the isotopic masses are pretty close to a whole number. And then the whole number is just relating to that mass number. There's another mass spec question similar to that one later, so we'll look at hopefully another example or two of that technique. So some elements like iodine just exist as one isotope. So iodine only exists in nature as iodine-127. I want to almost say that we probably could have guessed this in a minute, but what is the isotopic mass of that iodine-127? Well, if you know iodine's 100% iodine-127, all we have to do is look at the periodic table. The average atomic weight in the periodic table says 126.9047, this number here. And so because that's the average, so if you look at the equation, the sum over all isotopes, if you do 100% times the fraction of that isotope, then you get the average atomic weight that we put on the periodic table. So the key is that every average atomic weight that we come up with from that approach or that equation of summing up all the naturally occurring isotopes and their isotopic masses, that's what we're putting on the periodic table. And so I look at I circled the wrong number. I want to circle C. C is the right answer. B is just rounded weird to make those of us who can't see well mistakenly choose it, I guess. But 126.90447, that's the average atomic weight. That's the periodic table listed weight of iodine. That has to be its atomic weight. Now, choice D, you might go with D if you just thought iodine-127 would be exactly 127 AMU. That's not how it works. These isotopic masses are precisely determined. Only one mass is exactly the number of AMU, that's carbon-12, and that's by definition. So carbon-12 is defined to be exactly 12 AMU, but every other isotopic mass is going to vary a little bit off of a whole number. Now, I said you probably could have guessed it would be iodine-127. Like we told you in this problem that it was I-127, but you probably could have guessed that for a mass of 126.9, that the only way you're going to come up with that average atomic weight is that nearest whole number of 127. So I think we could have guessed 127 would be the mass number. So let's remind ourselves the mass number we write up top or give after a dash. The atomic number is when we get off the periodic table. Iodine's element number 53. So this is our atomic number. We get that one from the periodic table. That's a good question. So let's think about that for a second. So what really defines an element, like what makes iodine special compared to, bromine or tellurium or xenon? What makes the elements unique is their proton count, the positive count. The neutral count doesn't change too much of the properties. That's why our isotopes change neutron count, and that you still have basically the same element with the same property. So the atomic number, this is the number of protons. And so iodine would have 53 protons, and then the difference would be 74 neutrons. Okay, so if we know like an isotopic mass, we can probably predict the mass number from which we could calculate the neutrons versus protons if we knew what the element was. I mentioned that we would probably see a dimension problem of cubic dimensions. This is an example of that. So we want to calculate the volume of a pole in liters given these conversion factors here. Now, I want to do the problem kind of like two ways. And the second way I think will be easier and maybe the way you might be thinking right now of doing it. So if you're thinking there's probably a shortcut, there probably is. But method one, I'm going to calculate just the meter time meter time meter. I'm going to go ahead and calculate the volume of the pole in cubic meters, just given the values here. Just so we can go through calculating using cubic dimensions. So I go 5.00 times 8.500 times 2.50. So I get 106.25 cubic meters. All those were 3 sig figs, so I don't want the sig figs to be too confusing, but we could round or keep the extra. I'll keep the extra for now. And so if I want to then convert the volume of the pole into liters, I could be thinking of using the, 1 cubic centimeter is 1 milliliter, and then 1,000 milliliters is a liter. And I just somehow need to get from cubic meters to cubic centimeters. And so if I try to use dimensional analysis, starting with 106.25 cubic meters, and I go to do this conversion, because I think we all know there's 100 centimeters in a meter, but there's not 100 cubic centimeters in a cubic meter. I have to cube my entire conversion factor. And so because I have a cubic meter, another thought here could be that if you're looking at your conversion factor, I really need to convert cubic meters here so that it cancels out. So I need a cubic meter, so I have to cube the conversion factor. So 1 meter by 1 meter by 1 meter in centimeters would be 100 by 100 by 100. So if you're cubing a conversion factor, if you're using a conversion factor that you have to cube the conversion factor. Yeah.
Would you also have to cube the 106.25?
No, because that's already been like cubed, you know what I mean? So that's already that number in cubic meters. So it's 106.5. So this would be a pretty big volume. So think of what 100 cubic meters might look like. So 8.5 meters. I mean, it's even longer than the dimensions I'm kind of showing. Okay, so we do this times 100 cubed. And now, again, just make sure you do 100 caret 3, not 100 E3. That's another mistake sometimes we make, is doing 100 to the power of 3 versus 100 to, times 10 to the 3. So we have to make sure that we do it this way. Or 100 times 100 times 100. To be honest, that's what I do half the time, because most of the time I'm using like my iPhone. Obviously you can't use it on the test, but if you're just using like an iPhone, it's just easier to be 106.25 times 100 times 100 times 100, sometimes in finding the caret button. And then that gets us to cubic centimeters. A cubic centimeter is a milliliter, exactly. And then 1,000, not equals yet, one more step. And then 1,000 milliliters is 1 liter. So I think that would work out to answer C. So we got 1.06 times 10 to the 2, net times 10 to the 3. So that's one way of solving this problem, is just converting and calculating the volume in cubic meters, and then converting those units over into liters. Now I mentioned there's probably an easier way to do this step. So method 2 might have been, and maybe you were thinking this, if you were thinking this is probably a good thought, is why don't I just directly calculate the volume in cubic centimeters? Why don't I just get that volume in cubic centimeters right off the bat? Because I could do 500 centimeters. So instead of 5 meters, that's 500 centimeters. Instead of 8.50 meters, that's 850 centimeters. I'm just multiplying and converting meter times 100. And then times 250 centimeters, each of those with 3 sig figs. So if I do 500 times 850 times 250, was anybody thinking that in their head, that I could have gotten the volume and cubic centimeters right off the bat and skipped the cubic conversion? And so if you're thinking that's a good thought, and so I get, well, it's a bunch of units. I'm going to switch my calculator. If you don't know this, the second button on these TI-30s, you can go into scientific notation mode. So that's 1.0625 times 10 to the 8. So you can switch your calculator into scientific notation mode if you don't want to do all the counting and maybe make a mistake. And then to go back, you just hit the second button, go back to floating mode. And so now I just need to convert this, which is directly a milliliter. Oops. So a cubic centimeter is a milliliter. So that's an easy conversion. Then 1,000 milliliters per liter. So we're just dividing by 1,000. So that's, again, coming up with 1.06 times 10 to the 5. Okay, so it's two different ways we can get at calculating this value here. The second way is probably faster, it's probably easier, but it doesn't necessarily show how to do the cubic conversion. I just want to make sure that we kind of showed and went back through that 100 centimeters cubed is equal to 1 cubic meter. Yes? Sure, which one? Yeah, chromium 6. Sure. So for chromium 6 nitrate, so the key is that this here is telling you the charge of chromium, that's chromium 6 plus. So that's what the 6 means. And then nitrate is just the NO3 minus ion. And so we just have to, an ionic compound should be charged neutral, so I just have to take the 6 plus, and I have to come up with a 6 minus, so I need there to be 6 of the nitrate ions. So this would be chromium, NO3, parentheses around the NO3, 6. So if we had like chromium 6 oxide, that would be chromium 6 plus, oxide's a 2 minus, so here we'll have CrO3 because of the 2 minus. So the keys are knowing that the first group, the alkalis are +1, the second group, alkaline group's +2, aluminum's +3, oxygen's group -2, nitrogen -3. So nitrogen -3, oxygen group -2, fluorine group -1. That's periodic table placement, getting to that stable count of electrons.
You may have said this before, but will we have to memorize how many fluid ounces are in a milliliter? Or
No, like any conversion factor that's like a non-SI unit will give you. I mean, the only conversion factors to really know are the prefix conversions, like centimeter to meter. Let's go here and then back over here. Yeah, so 6 plus for chromium nitrate. Oh, you mean for here? Well, like it's group 1. Think like sodium needs to lose 1 to get to the noble gas count, so that's +1. Magnesium needs to lose 2, so it's +2. Nitrogen -3. Oxygen group's -2, halogen group -1. There's like an anion summary page that has those on it too. Yeah, I threw that into the like probably not on the test. So like things like zinc, if we say like zinc chloride, we usually say zinc chloride, not zinc 2 chloride. I don't know why. There's just something in the book that kind of like lists zinc as zinc 2, and then there was a while when we actually would put that on the test, and then I think we've discovered that that's kind of silly. But like you will see this in the lab that we'll call zinc chloride just zinc 2 plus. It only forms a 2 plus ion. No, zinc, zinc, silver, and lead. You'll see a lot in lab. Probably not something to worry about for the test, but silver's always a +1, lead's a +2. Mercury's goofy. I wouldn't worry about mercury for the test. It'll come up again in chapter 4. Hopefully we'll get it there. And then aluminum's a +3. It's in that goofy group where it's one of the only in its group that forms ions, and it's of the +3 charge. Sig figs, not sure if we're good on these. Hopefully we are. But just looking at 50 plus 74. Now the key would be just assume these are all numbers subject to the sig fig rule. So 50 just has the 1 sig fig, 74 the 2. When we add and subtract, we have to look at the placeholders. And so this 10's placeholder is of higher value than the 1's placeholder. So I'm going to round this to 120 because of 50. Now think of why this is. It's 50 plus or minus 10. That plus or minus 10 is what's wrecking this math problem. So it's the plus minus 10 here versus the plus minus 1, and the plus minus 10 wins out. So we round to 120 plus or minus 10, which is 2 sig figs in the number. Now something I think that confuses some folks is when I look at the result and then say it has 2 sig figs, It's like you have to apply the sig fig rule for addition, and then you just count the sig figs you happen to get. So because the 5 and the 7 gave me an extra digit, I ended up with 2. So I think sometimes when we say how many sig figs does this result have, makes some students think I gotta count 1 sig in 50, 2 in the 74, I should round it to 1 sig fig. No, we don't count sig figs when we add and subtract. We look at placeholders, and we just happen to give the sig figs that we end up with. In this case, there's 2 values that are significant. Multi-step problem, we just have to multiply, use the multiplication rule, and we multiply, so that would have 3 sig figs because it's a multiplication step. Here's an addition step. I have to just think real quick. Calculator says 5, but it's 5.00 to proper sig figs to 3 sig figs. So 3 sig figs divided by 3 sig figs should have 3 sig figs. In terms of the math, 16.0 times 1.25 is 20 divided by 5.00 is 4 in my calculator, but I have to add on 2 zeros. Now think of why this is important. If you're doing work in the lab, there's a big difference between saying 4 grams per milliliter and 4.00 grams per milliliter. Because if we only determine this to 4 grams per milliliter, it could have been 3 to 5. So maybe it's really 3.51. Maybe it's really supposed to have been 4.47. There's a big disagreement on what the density is. Imagine you're going to court and you're a data scientist trying to prove something that had to be 4.00 versus 4 to some precision. That's where this kind of comes in. If we want to precisely state how confident we are in our results, 4.00 here would be perfect. If somehow this were just leading to the units of grams per milliliter, then that would be maybe like a density. So just thinking here to 3 sig figs. Now, the last example on this page is maybe tricky because it has scientific notation. And so scientific notation is slightly complicated just because maybe it's better or it's more obvious if we write these out on what the problem is or how we come up with the solution. So if I just write those out as their actual numbers, I think you can see that pretty clearly it's a pretty easy sig fig problem if we have it written out this way. 47400 plus 78700 goes to 126100. How many of those digits are significant? 3 or 4? The answer is all 4. So we have 4 significant digits here because I'm just applying the rule that I have to report it to that placeholder. That's the hundreds placeholder. So the 126100 should be good to the hundreds placeholder. Now if I use scientific notation, now this is where this problem becomes tricky. If you just put this in your calculator, it looks like hundredths place plus hundredths place should be rounded to the hundredths place. So when you put this in your calculator and it says 1.261 e to the 1, 2, 3, 4, 5, you might be thinking that you should round here, but that's not the right placeholder. That's the placeholder of the hundredths place relative to the exponent of 10 to the 4. I doubt you'll see scientific notation problems embedded into sig fig problems, but if you do, my advice is just write out the numbers as their regular numbers, and then think of which digits are significant from what we were told in the problem, and then just do the math accordingly from there. So scientific notation, I think, is only tricky if you keep the digits in scientific notation. Just write everything relative to a common decimal point, and just think of the ordinary arithmetic from there. Let's do some naming. There's actually a lot of naming that we could do too. I have a couple extra packets, so we might go over into the start of the lecture on a couple of examples of naming. But sodium hydrogen phosphate, so we just have to think hydrogen phosphate is a hydrogen ion added onto phosphate, which ends up with a charge of 2 minus. So hydrogen phosphate has a charge of 2 minus, dihydrogen phosphate of -1. Trihydrogen phosphate, H3PO4, wouldn't be called trihydrogen phosphate. We call that phosphoric acid. So once we get to neutral, this is named as being an acid. We call that phosphoric acid. Now, an interesting question is this an acid? Is HPO4 2 minus an acid? Because it's not named as being an acid, right? It's named as hydrogen phosphate ion. We name it for still being an ion. It could behave as an acid later. That's a very tricky question to answer here. But technically speaking, like HPO4 minus, H2PO4 minus, those are technically acids but they aren't named as being acids. We don't name something as an acid until it's charged neutral, okay? And so we only consider naming acids as acids if the overall charge is neutral. So we fully neutralize the charge, H3PO4, an acid. This thing here still has a charge. We still name it as an anion with that phosphate nomenclature. And so if we have sodium as our counter ion, sodium plus to the 2 minus, how many sodiums do we need? 2. So we need 2 pluses to balance out the 2 minus. So Na2HPO4 would be sodium hydrogen phosphate. This kind of was an example like earlier, chromium 6 plus, sulfide is a 2 minus, it's in the oxide group. So that'd be Cr with 3 sulfide ions, so CrS3. Now I'm just lassoing out and showing that we don't include the charges in the formula, so just making sure that we just show the elements and the subscripts in the formula. What about cesium? Well, I just gave the element away, but cesium is what Cs plus is. What about OH minus? That's cesium hydroxide. What about nitrous acid versus nitric acid? So nitric acid is HNO3 because that's derived off nitrate. Nitrous acid must be derived off of nitrite, which is NO2 minus. So we just drop one of the N's, the O count to 2 from what was 3 in nitrate. So we have to know NO3 minus is nitrate. So nitrite is NO2 minus, H plus in front. So HNO2 is nitrous acid. C4H9, the hydroxyl group. So this is an alcohol of a hydrocarbon. And so what's C4H10? So propane was the third. That's maybe the only tricky one is propane versus butane, but it goes methane, ethane, that's easy. Most people know that. Propane's next, and then butane. So this is butane. So this is butanol. So now, determining ionic versus molecular compounds is somewhat useful. So the first 2 examples were ionic compounds because they're metal nonmetals. That's how I know that. So they're named in the IC nomenclature system, and these are all molecular compounds. They're all molecular compounds. Well, actually, this is an IC as well. The aluminum here, that's an IC. But the other examples here are molecular compounds. Molecular compounds are the non-metallic elements bonding together. Al2CO3, how do we break this one down? Well, there's a few ways. One starting point is that carbonate has to be a 2 minus. That's just our simple memorization. The carbonate, CO3 2 minus is carbonate. There's 3 2 minuses, so that's a 6 minus. So I have to have a 6 plus from the 2 aluminums to balance out the charge to go to neutral. Remember, there's no charge shown for the collection of atoms, and a compound should be charged neutral. And so that tells us that we have to have a 6 plus from the 2 aluminums, 6 plus 3 each. We also know based off of aluminum's periodic table position, it should be a +3, that's aluminum's common charge. So this is just the compound aluminum carbonate. Is anybody from a different country and wants to call it aluminium? Anybody think that? That's an accepted name for aluminum, is aluminium as well. So you can call it aluminium carbonate if you wish as well. That's perfectly acceptable name. And so what about boron trichloride? This is that category of binary. So when I have 2 elements and it doesn't look like a hydrocarbon, doesn't look like an alcohol, it's not ionic compound. This is a binary molecular compound. I just made up that lingo, so binary molecular compound. And so that just means the system is the first element must be one of them, and there must be 3 of the next element. So that's really easy, boron trichloride, BlCl3. And then nonane is maybe the only tricky C1 to C10 hydrocarbon, just because nonane and a 9-sided octagon is pretty uncommon, but that's the C9. So nona is the prefix for 9, octa is 8, deca is 10. So 9's the weird one that maybe is hard to remember. But then the hydrogen count shouldn't be 18 because I have to have CH3s on the end plus CH2s in the middle, so it has to be 20. And so if I'm not sure, just sketch out one of 2 ways. The simple way is to do this thought. I have CH3s on the start and end positions, then I have to have 7 CH3s in the middle to get the 9 total carbons. So that's 14 plus 6. So that's 20. So the only hard part with the hydrocarbons is getting the right count for hydrogen. If you notice, it's 2 times the number of carbons plus 2. Because it's like doubling, it's like CH2s in every position and just doubling the ends for CH3s. And the whole idea, if you recall, is that carbon just wants to have 4 total bonds. So carbon wants to have 4 bonds. And so CH3s on the end give the end carbons 4, and CH2s in the middle give those middle carbons 4 total bonds. What about this question here? So we have aluminum oxalate, Al2, C2O4, 3. Now, this oxalate ion, we didn't have to have this in our nomenclature. In fact, it wasn't anywhere in our nomenclature, but we're told aluminum oxalate has this formula. So knowing this is the formula for what we call oxalate, can we deduce the charge of oxalate? You know, we know aluminum's a 3+ from what we talked about on periodic table placement. There's 2 aluminums, so there's a 6+. And so I have to have a total 6- from the 3 oxalate ions. And so that makes each of the oxalates a 2-. And so here, this is a problem where we're telling you the name and the formula allows us to like deduce what the charge has to be on the oxalate ion. So what we can determine is that C2O4 with the 2- charge, that this is what we call oxalate. And then what would iron 2 oxalate's formula be? So with the same oxalate ion, if we pair it up with iron 2+, this goes 1 to 1, 2+ to 2-. You know, so it's just like deducing charge from the nomenclature system and applying that accordingly. You know, there's a couple examples on the practice quizzes with like cyanide ion. I don't think that made its way onto our equation sheet. So like this is cyanide. But if I tell you that like iron 3 cyanide is this, you know that's iron 3+. You know it takes 3 cyanides to counterbalance it. You can deduce the charge. Then you could say, well, what's calcium cyanide? CaCN2, because you know calcium's a 2+. So given a formula and an ion you don't know, where you get the name, helps you deduce the charge of the ion, then you can pair it up with some other metal if you know its charge and put it together and work out the nomenclature. So you might see questions that kind of test the systems of nomenclature. We can even say, well, what's oxalic acid? I'll get your question 1 second. So oxalic acid, if you neutralize this with H+, that must be the formula for oxalic acid, just H2, C2O4.
So what's going to be like given on one of the sheets like that for us?
Yeah, like if you go to the module, we went through this at the start of the video, but if you go to the module for the practice exams, it has the useful info page. And it doesn't have a lot of the constants and conversion factors you may want to have, but we would give you those in the question if you need them, or you can apply, you probably don't need them as well. Possible.
Remember like the 8s, us, it's,
Yeah, all that. So the nomenclature you have to know. Yeah, so the nomenclature.
that's so important. I know the charge of that, stuff like that.
Yeah, you have no sulfates at 2-, carbonates at 2-, phosphate 3-. Yeah. But the drop in O goes to ite. That's a very simple system. So if you know phosphates PO4, 3-, PO3, 3- being phosphite, should be a pretty easy one.
So you have 8 us.
Well, 8 ites, the us's is like an acid. So if you go to the acid form, the ites go to us acid. The very first part of the video, I'll go through some examples of this. And I'm going to put up like a 2-part video. So once I get into some new chapter 3 stuff a little bit today, I'll probably continue for about 10 more minutes on review. We have to get into some chapter 3 stuff just so we don't fall behind for midterm 2, unfortunately. But once I switch over, I'm going to switch videos. So, yep.
Like organic compounds like butane and etc. Organic compounds like molecular compounds like all of them.
The only things that I would know are just the base formulas for like methane, ethane, propane, etc. Just like CH4, C2H6, C3H8. Once you get to butane, you get to C4H10. The book has like it could be N-butane versus like isobutane. You get the pentane, you have all these isomers. Don't worry about the isomers of hydrocarbons. Just think about, you know, like we really just want you to know that it's C5H12 for pentane, it's C16H14 for hexane. And if you think of the arrangement of carbon just being linear, that's fine. If you think of being carbon to carbon in a row of 6, that's perfectly fine. If you look in the book, people start naming some goofy compounds and getting into some organic nomenclature. Don't worry about that. They'll get into naming like ethanoic acid and propanoic acid. Don't worry about that naming either. The only carboxylic acid group we talked about was acetic acid, which is a CH3, COOH. We talked about how the COOH group is an important acidic group. So if you see anything with COOH, you'll know that that's acidic. That's more of a topic for chapter 4 when we get there, for helping us recognize that later. So if we went through the proton-neutron count, we actually had an example earlier with iodine, but iodine 127, this is the mass number. That's the sum of the protons and neutrons. We have to look up or know that we can look this up off the periodic table. That's the atomic number for iodine. That's the number of protons. And so the difference here of 74 is our neutron count. And then if we go to a net negative charge, we can exchange electrons. Electrons are light, they're on the outside of the atom. So if we add electrons, go to negative charge, take them away from the atom, we go to a positive charge. So iodine 127 with a net negative charge has picked up 1 extra electron, 54 electrons. We have 1 more electrons than the positive particles. So our charge -1 is from from the number of protons, 53, minus the number of electrons, 54. So the charge, sorry, it's sloppy, but the charge is equal to the proton count minus the electron count. So think about any atom this works. So think about calcium. Calcium's element 20 protons. I need to turn this on auto. I keep double tapping this stupid pencil. It keeps going to erase mode. But so 20 protons. If I take a 2+ ion of calcium, I have 18 electrons because I've taken 2 away. To get to a net 2+ charge, I've taken 2 electrons away. And so my +2 charge is obtained from 20 minus 18. So plus charges, I'm taking those electrons away. Negative charge, I'm adding those electrons into the atom. So anions have electrons absorbed into the atom. Positive charge, electrons removed from the atom. All right, sig fig question. I distinctly remember this semester. This is such a silly question. A lot of these sig fig questions are just very systematic and obnoxious. And you just have to be very precise with the math here. Let's look at this step first here, the 20 plus 1163. Now, the part I think that confused everybody was if you had a balance that went to the nearest ones placeholder for the 1163, why would it not have been to the nearest one placeholder for the 20? And the answer is you just have to take 20 centimeters to only be 1 sig fig, and you have to not worry about why that is. The implication could be that a different scale was used for the one value versus the other. This is kind of like the example in class. If you think you have $1,000 roughly, and I give you like $3, you don't exactly have $1,003 because you didn't exactly know that you had $1,000. You'd have to precisely know you had $1,000 to at least 4 significant figures to at least that number of precision to add $3 to that to get precisely 1,003. It's that example here. So the plus 20 here must have just been a poorer tool or a different type of tool that was used to measure the 1163. So just know when we give you 20, we really mean 1 sig fig. And we are being careful when we give you the sig fig. So imply the number of sig figs from what 20 means without any indication of that 0 being significant. So this is just 1 sig fig. So we see 20 centimeters, that's just 1 sig fig. So I did this math here, it goes 1183 with just 3 significant figures. Now, whether you round it or not, I wouldn't be too worried about that for the exam. You can round it if you want. You could keep it as 1183, but just know that it has 3 significant digits. So it's probably better to not round it than to round it, but it's better to get the answer right too. So I don't really care what you do in the test as long as you get the right answer. But it's just 3 sig figs. I'm going to eventually do a multiplication step, so I need to look at the sig figs on my second step. I'm subtracting 15.160 minus 0.00863. And so that's 15.151 to that placeholder, because I have that placeholder minus more placeholders. I round to the quantity of placeholders that's greater in numerical value. So I round that to the thousands placeholder. That's 5 sig figs. If you round that or you don't round it, it's not going to change the answer. So it doesn't really make a difference on the answer to the question if you round it or not. If you're in a lab example, maybe don't round it in lab. But for this here, 5 sig figs times 3 sig figs, the end result should have 3 sig figs because I'm doing a final multiplication step. So to me, the sig fig rules are pretty simple. We add and subtract, it's all about where the placeholders are. We round to the placeholder and we just have however many digits are significant on the other side of that placeholder. And then we multiply and divide, we just count sig figs. Multi-step problems, apply those rules in the order we do the math. Yeah, so addition and subtraction, I mean, I'm looking at this 3 versus that 2. Like that's the important placeholder difference. So when I do this math, I didn't stack it, but if we do, like we might do this here. So we're just doing that step here. Let's kind of wrap up maybe our exam review with this here, maybe a couple quick nomenclature questions following this. But who's credited with discovering the electron? The electron was studied by the cathode ray tube experiment. We had a cathode ray that was deflected by a magnetic or electric field that showed that you had a negative particle. That negative particle was the discovery of the electron. This was by Thomson with the cathode ray tube experiment. What subatomic particle was discovered first? That was the electron. This probably is something that's never been tested, though I think this is really interesting. Like, what do you think would come next in discovery? If the electron's first, it's the outer part of the atom, so it's easiest to eject an electron. The next particle you might just imagine would be discovered next is the positive particle. So the proton comes next, and the neutron comes last. I wouldn't worry about this too much. I used to talk about this a little bit more, but you would imagine that the next easiest particle to discover would be the charged particle in the nucleus. The hardest particle to detect is that neutron. I think I do remember mentioning in class, because I think I mentioned the year 1932, I believe was the year the neutron was discovered. And I just think that's like so crazy recent, right? For our understanding of the periodic table, that's like less than, well, a little bit more than 90 years ago. It used to be a little less than 90 years ago. Anyways, so what particles did Curie discover through the radioactivity experiments? And so is the alpha particle, the beta particle, and the gamma particle. And the alpha, let's start with the beta particle. This is the electron. So that's the same type of electron particle that was discovered in the same way. You had a ray of, you had a beam that was being deflected by the magnetic field in the same way that the cathode ray tube was being deflected. So this looked just like the cathode ray tube electron. So the beta ray is the electron. The alpha particle is the massive amount of charge. It's the helium nucleus, the helium with the 2+ charge. It's the helium nucleus falling off of a radioactive atom. And then the gamma ray is a packet of light, a very high energy, even greater energy than X-rays. I think the key detail here is that this particle here was then used in the next experiment. So the alpha particle, that massive particle, was the cannon being fired at that thin sheet of gold, thinking it would go straight through, but a lot of the particles are deflected, proving the existence of the nucleus. So Millikan and so Rutherford's alpha particle scattering showed the discovery of the nucleus, and Millikan, through the oil drop experiment, determined the charge and mass of the electron. So Thomson discovers the electron in the cathode ray tube experiment. Millikan discovers the charge and mass of the electron through the oil drop experiment. Through suspended oil droplets with the charge, deflected by an electric field, and they could determine the mass and charge of the electron through that experiment. And so oil drop Millikan, charge and mass of the electron, the actual discovery of the nucleus through the alpha scattering experiment of Rutherford, shooting the alpha particle from Curie's experiment at a piece of gold and seeing that they all didn't go straight through the gold. All right, this is the quiz from over the weekend. I just wanted to look at a couple naming questions that are relatively quick to look at here. So just aluminum oxide, So Al's a 3+, oxide's a 2-, and so this is probably easiest done this way here. Al2O3, we can cross multiply down because we get a 6+, 6- to balance out our charges. Sometimes you'll see the test call this the empirical formula. So like it may say, what's the empirical formula for aluminum oxide? Don't let the word empirical formula confuse you. It's just saying, what's the formula? So we always represent formulas for ICs by the simplest ratio of the atoms. And for aluminum and oxygen, this is like the only compound that forms. If you look at carbon versus oxygen, you can get like CO over CO2. If you look at N versus O, you can get NO2, N2O, NO2, N2O5, N2O4. You can get all those goofy molecules. That's where we use the binary system to name all of those. So the key detail, ionic compounds, you get one compound, the simplest ratio from their known ions and their charges. And the only difference, though, might be the transition metals. You can have different charges. So we use the Roman numeral system to indicate charge. So we don't have to have anything memorized for the transition metals. A couple other quick nomenclature ones. So like dinitrogen pentaoxide. So that's an example of that binary system here. So it looks like E. And don't let the pentaoxide versus pentoxide confuse you. If you look at some of these questions and want to go over these in more detail, if you just go to this quiz on the daily quizzes, it has a key and there's also a video solution. So I just wanted to look at the quicker named examples on naming. Cyanide's probably, again, not one you probably had to have memorized, but if you know it's CN-, this is pretty easy, right? It's just Fe2+, and then CN for two of them. Oh, I'm sorry, that's cerium, not iron. So cerium 2+. And now, one of the reasons why I wanted to say this one here, we don't talk too much about the lanthanide and actinide elements, but you don't need to know anything special about Ce other than that it's cerium. And it's definitely not chromium. So I wouldn't worry about that too much either. Most of our examples will come from the first row, the transition metal, if we want to do transition metals. But this is clearly not chromium, so Ce, Cn2. Magnesium dihydrogen phosphate. So dihydrogen phosphate is this, but with a minus, because I have two H+ on the original 3- ion. I'm almost a H3PO4 neutral, but I'm not quite there. So magnesium 2+. And so I go two of the minus ions to counterbalance the charge. So I go magnesium, H2PO4, 2. Strontium and nitrogen, what's the common compound here? Well, again, that's a weird one. Strontium, we know that one. That's right underneath calcium, that's a 2+. Nitrogen's a 3-. And so this would be nitrogen 2, strontium 3 to get a 6+, 6-. So here we're just using the common ion charges from the periodic table. So we can do this for the group 1 + 1, group 2 + 2, alkalis +1, calcium's groups +2, aluminum's +3, nitrogen 3-, oxygen 2-, halogen group 1-. Just looking at periodic table placement to come up with those counts. Now, I just like showing this calcium bromide. It's not dibromide. Sometimes we get tricked into some silly answers here. It's definitely not calcium bromine. It's just calcium bromide. Just for the name of calcium, calcium ion, and then here it's Br- and Br-. Br2 is not two bromines bonded together, it's two bromide ions. It's a simple monoatomic bromide ion, and this is what we call bromide. So that's calcium bromide. Just making sure we have a good picture of that. The calcium, yeah, so. Well, it's the ionic compound nomenclature system is that you go name of the cation followed by the name of the anion. And then that's it. You need to use the monos, dis, tris, tetras. That system's for binary molecular compounds, and this is a binary ionic compound. So for ICs, ionic compounds always go cation followed by anion. And the reason why is that calcium's always a 2+, bromide's always a -1. It has to be CaBr2. Like we don't have to give ethyl bromide.